Hi, my name is Choudhary, and today I'm excited to share with you our latest paper, Adaptive Electrical Muscle Stimulation, along with my collaborators done at the University of Chicago. Even in the midst of advanced interactive technologies today, like videos or interactive tutorials, acquiring muscle memory with new physical skill is still something we do mostly by watching and copying movements. However, in the past years, we've had the emergence of electrical muscle stimulation in HCI. Muscle stimulation is a technique that sends small electrical impulses to the muscle to move users' bodies. This technique promises a world in which we might be able to download interactive assistance to our own body, so that, for instance, when learning the piano, we can play the melody directly from your hands. In fact, our lab did that in CHI25. Let me play a video for you. As you just witnessed in this video, you can actually download a piano melody into your hand and have muscle stimulation play the melody with your own fingers. Najima also explored this concept, but instead of melodies, the user can download techniques such as staccato or legato. In fact, some researchers have shown that muscle stimulation helps with learning new physical skills, such as playing percussion or learning how to bowl, when compared to no muscle stimulation. So altogether, they point to a world that we strongly advocate for, in which when practicing and learning physical skills, feeling our own muscles moving might be more powerful than just seeing other bodies. This might alleviate many hurdles such as cognitive load, processing visual information, potential distractions, all while trying to copy movements, but also for visual accessibility. If haptic learning world is so desirable, then we must ask the key question. How shall we help design muscle assistance? What does it do? How does it help me? And how does it understand what help I need? So let's take a look at a state-of-the-art for the interactive EMS systems. When we see how these assistive systems help their users, we realize one commonality in their design. They all operate in the same way, meaning they all do the work for the users by demonstrating. We propose a different strategy, where the system adapts as the user gets better at learning. So instead of only demonstrating the correct melody, as seen here on the left, the system adapts to the user's learning. And we do this by tracking the errors during the learning process. Let's say that here, the user manages to learn about half of the melody, but they're still struggling to remember the note that comes after E in this section, which is a D. Instead of showing the whole melody, the system lets the user play and only corrects them when a wrong note was played. This was done by repelling the fingers and then playing the correct note using muscle stimulation. This change occurs because the system adapted to the user's learning curve, and in this case, the system went into what we call the correction phase. As the user gets better, with errors going down, the system switches to yet another phase, the warning phase. Here, the muscle stimulation only warns the user by repelling their hand when the wrong note is played. The rest is still up to them. To understand if our novel adaptive approach will lead to better learning outcomes, we decided to conduct a user study. Using our custom-made piano learning tutorial, where individuals actuate 3 of their fingers, which are resting on a bass, so as to involuntarily play 3-note piano melodies with muscle actuation. Our study follows a standard pre- and post-test design. First, we administered a pre-test, which weeded out folks with significant musical skills or piano players, so only novices were qualified. Then, we moved to learning trials, where participants learned piano melodies with one of our 2 conditions. The first of which was the static approach. Here's an example of a piano melody. In static approach, we demonstrate the entire piano melody with muscle stimulation. Then, we wait for the user to recall it all by themselves, and regardless of the user's performance, it will demonstrate the entire melody over and over and over again, and this process continues and only stops when the user is able to recall the melody all by themselves with over 95% accuracy. And for the melodies that we used, which were fairly long, this means only 1 mistake was allowed. This was a very challenging learning task. The other condition is our adapted muscle stimulation approach. Here, the user would receive 3 types of assistance, depending on the errors that they had while they were playing. If they had more than 50% of the melody long, the entire melody would be demonstrated just like in the static muscle stimulation condition. However, as they improve, in which they make between 25 to 50% mistakes on the melody, the muscle assistance will turn to the corrective mode, in which it will let the users play notes and it only intervenes when they make a mistake. If that happens, the muscle stimulation will pull the hand away from the keyboard and then push the wrong one onto the right note using muscle stimulation. When the user is close to mastery and only about 25% errors are made, the muscle stimulation switches to an only warning mode. And during this, when the user makes a mistake, all the EMS does is pull their arm away from the keyboard. And then it's still up to the user to play the correct note and then move on to the next few notes. Okay, so now that we have our condition accomplished in one of the cases and our users have reached mastery, we have stopped learning trials. So we take out the electrodes and then we send the users to take a break for at least 1 hour. And then we call them back for a final trial. During this, unassisted, they try to play back the melody from memory. At this point, we count how many mistakes that they made, and this becomes our final post-test score. Once a user is done learning with one method, we let them take a break for several hours, and then we move on to the next condition that they haven't experienced yet, in a counterbalance order, and we provide them a new, totally different melody of similar difficulty. Alright, so what did we find out? First, we found that participants performed better with the adaptive condition. This means that when they came back hours later to perform the melody unassisted, we saw significantly less mistakes after they learned this melody with the adaptive muscle stimulation. This is a very exciting result to see, but also, we found that after trying both methods, participants overwhelmingly preferred the adaptive method. When asked about their experience with trying to learn piano melodies with these different approaches, we found that participants thought that the EMS enhanced their learning experience. Particularly, many of them use the term, "it's more engaging." Some of them even refer to it as a way to reduce guesswork, or that it helped them identify and improve their mistakes along the way. However, it's not only benefits with adaptive EMS. There's still some kinks that we need to work out and think about. For example, this participant saw that adaptive EMS needs a little bit more context when it comes to providing corrections, because it's a little difficult to understand what note is being corrected compared to the previous notes. And also, that it can interfere with own movements when the muscle stimulation randomly inserts itself into a combination of notes. We took our participant suggestions and proposed an adaptive EMS application. Here, the user is learning to spell Morse code with adaptive EMS. They want to spell the word mind, but they make a mistake at the last letter D. Adaptive EMS warns the user of the mistake by pulling her finger away, but instead of just demonstrating the last letter D, it repeats the entire word mind using Morse code to provide more context for the error. We can also use adaptive EMS to teach users new instruments. Here, she's playing theremin by controlling the pitch with the right hand and the volume with the left hand. Because both hands are occupied, we don't want to interfere with the hands when showing a correction. Instead, we can use other parts of the body to inform the user of a mistake that they make. Here, we do that by redirecting the head to the hand that made the mistake. We can also teach more complicated tasks that involve multiple limbs. Here, the user is learning to control a robot arm with a joystick and foot pedals. We see that she steps on the wrong foot pedal, and the adaptive EMS warns her by simulating her arm, and then shows a correct sequence. Over the last decade or so, the discussion of muscle stimulation in academia has become more and more prevalent. However, we initially only saw the use of muscle stimulation for immersion in virtual reality. We have now begun to see the use of muscle stimulation more and more for physical assistance. For example, muscle stimulation can be used to guide physical tasks such as spelling and sign language or drawing a picture. Further, we see how it can be used for enhancing or learning new physical tasks such as bowling or playing the piano. Beyond just learning, last year at CHI25, Romain and Yoon presented a work that showed that muscle stimulation can actually reduce cognitive load when performing a physical multitask. And now, we're bringing to you our work in adaptive muscle stimulation. This focus lies not just in our work, but also in 4 other papers brought to CHI this year, which we were super excited to see. Thank you so much for listening. Please check out our paper for more details.